Hello, hello, hello.
Hi.
Everybody. I'm Brian Beckman, and I'm here with Rich Hickey today. Rich is the creator of Clojure. And Rich, you're unaffiliated or independent, correct?
I'm an independent
Yes.
consultant.
What's some of your background in computing and language design and that kind of thing?
I've been working as a professional programmer for a couple of decades, specializing mostly in broadcast automation and scheduling systems. Also the National Exapol and various machine listening kinds of problems.
Oh, very good. So hardcore, real-time.
Yeah, a lot of time.
Throughput. Yeah. Okay. Good. Well, I'm just a country physicist who dabbles in programming, but I've been using Lisp for, I don't know, I think I discovered Scheme around 1978 or 79 and fell in love with it, and have deployed it in more strange corners of computers than you can possibly imagine. I guess my crowning glory would be sticking it in the kernel and using it to do page table replacement policies, policies. So I have a little bit of exposure to Lisp and Scheme, and let me ask you, well, first, why don't you just tell me what Clojure is before we jump into that?
Clojure is a dynamic language. It's a dialect of Lisp, and one of the interesting things about Lisp is that it supports dialects,
yes,
which is unusual compared to most other languages. And it's really founded on four ideas. One is that it be a functional language. So it's primarily functional, it's not pure,
right.
But it emphasizes immutability.
Okay.
The other is that it be a Lisp. And there's certain things about Lisps, in particular the syntactic extension capabilities of Lisps, that make them still unique, even though most of the other ideas from Lisp have been adopted by other languages.
Right.
It has an emphasis on concurrency. So a lot of the problems I've worked in, all these broadcast automation systems were multi-threaded, and they were done in C++ and Java and C#, and they're, basically that's too hard for me.
Yes.
So I was trying to make that easier. And the fourth attribute of Clojure is that it's designed to be hosted. So while it's implemented on top of the JVM and there's a port to the CLR, the fact that it's on top of those is not just an implementation detail. For instance, there are ports of Scheme and Common Lisp to the JVM. But that it's designed to be hosted. It's designed to let you touch the VM or the environment on which it's running, so that you can leverage all the libraries and everything else there.
Okay.
So it's specifically got support for calling Java objects and .NET objects.
Marvelous.
And
foreign
things like
function
that.
interface.
Well, but it's a lot less foreign than it is in those languages. So it's extremely transparent.
Now, does this mean that in the case of the CLR that you have access to all the reflection machinery and can...
that it sort of does that under the hood.
Under the hood,
right.
Okay.
So, but you can
As opposed to a Lisp-style model for CLR objects, or do you have that as well?
You basically, there's syntax for calling methods and calling new, and there's a dot special operator in Clojure, which is designed to provide a path to the host. Then there are macros that make that look quite Lisp-like.
Okay, good.
So a Lisp call would be open paren, foo XYZ.
Yep.
And a .NET call on some object X would be .foo XYZ.
It's still prefix notation.
It's absolutely still prefix notation.
Right.
And so you have access to objects and their methods and fields. And
why did you pick Lisp as a way to launch into something like this? Because you could imagine a dynamic language with support for, that's designed to be hosted, with support for calling into the CLR or the JVM that isn't Lisp.
Right.
Why did you pick Lisp?
Well, Lisp is still uniquely powerful in that syntactic extensibility area.
Okay, good.
So, for instance, if you have a language that you're using and you wish it had some construct that it doesn't, like for each or something like that. Let's just imagine your language didn't have it.
Right.
You would have to wait for the authors of the language to add it.
Yes.
And in Lisp, you don't have to wait. In Lisp, you can write any construct like that yourself.
Right.
So that kind of power is extremely useful. It ends up that in Lisp, you basically can write a custom language for every problem that you solve quite easily. And
a lot of people in our world call this metaprogramming.
Right.
And I remember when Eugene Kobecker created hygienic macros for Scheme,
Right.
gosh knows how many years ago now, that really opened it up.
Right. So all the macro systems are, the way that syntactic extension is implemented in Lisp.
Right, right.
They're called macros, and one of the problems with the word macros is people associate it with C macros,
Yeah.
which are sort of a very crude string substitution system. But real programmatic and hygienic macros are programs that transform programs into other programs.
Right, and this is enabled by the unique feature of Lisp that some people use the word auto-iconic.
Right, or homoiconic.
Or
right.
homoiconic. It just means that the representation for the program is the same as a representation for data.
Correct.
And you can transform the program a program itself exactly the way you would transform data structures.
Exactly, with the same libraries and the same tools.
Right.
That's correct.
And other languages that may be powerful in the functional world or the real-time world, such as ML. Languages like ML and Miranda and Haskell, they explicitly avoid auto-iconicism based on possibly on a paper by Wadler long ago that said calculating is better than scheming or something like this. But it does mean that metaprogramming is now a separate topic in those languages, whereas in Lisp you can use the language itself to modify itself. It's really wonderful.
That's right. And there's two aspects. One is that code is data. We call it code is data.
Yeah.
The other is that the evaluation strategy incorporates a step that says, at this point, I will call your program to help me evaluate.
Right.
So macros are a hook that's built into compilation or evaluation that allows your program that can do it. And everybody can write a program that transforms another program, transforms source code. The trick is that that's part of the evaluation strategy of the language, saying, I've done this, I've made a program that transforms a program, and when you see this, please call it.
Yes.
And the compiler will do that. It means that the evaluation is open to your programs, extension by your programs.
Now, does Clojure have more than one evaluation strategy, such as lazy versus strict, or does it have just one?
Clojure is strict.
It is strict.
But Clojure has sequences, which are an abstraction that can be implemented lazily.
Right.
And all of the Clojure core functions like map and filter are implemented lazily.
Okay, good.
So it's sort of a hybrid that way.
Right.
It's not lazy evaluation in the Haskell sense. On the other hand, the core algorithms for sequence manipulation have been written in a lazy style.
Well, and that's the main practical use of laziness is for infinite data structure or something, or streams.
Streams, right.
Yes. But it does mean that if your evaluation strategy is applicative order, that means specifically that you evaluate function arguments before you pass them to the function.
Correct.
Okay,
it's
good.
strict.
Good, super. Now, in what sense is Clojure functional, and in what sense is you said at the beginning that it's functional but not pure. Can you tell me exactly what you mean there?
Yes, I think functional has been applied for a whole spectrum of things. I think there's the Haskell meaning of functional, which is sort of the pure notion of function applied to absolutely everything in the language.
Right.
And then there's a notion of functional, which Lisps were claimed to be functional early on.
Right.
Only for the simple reason that functions were first-class objects.
They're values.
You could pass them. They're values, right? That you can pass around. And so those are the two ends. Somewhere in the middle, I think, is a style of programming that emphasizes programming with pure functions, in other words, functions that are free of side effects, that operate only upon their arguments, which are values, and that only produce values as results.
Right.
So that's a pure function, and so Clojure emphasizes the style of programming using pure functions, where Lisps traditionally have not. You could do it, but it was a choice. The key thing in forcing you to make that choice is to have the core data structures be immutable.
Right.
So they now can be treated as values in a way that mutable things cannot. So Clojure emphasizes functional programming by providing a set of core data structures, including those ones that you use to represent code. They're all immutable in Clojure, and they're also persistent, which is a special characteristic we could talk about.
Oh, that's interesting.
And because of that, it forces a functional style of programming because you cannot change them. So you have to write a function that produces a new value as a result. But there's no enforcement. If you write a function and you do I/O, then that's not a pure function anymore. And I don't preclude it, and there's no type system to preclude it. It's a dynamically typed language which just respects the programmer's right to do whatever they please.
Yes, yes. Well, that's the last dynamically typed language that I can remember in the sort of Haskell genealogy is probably Sassel. I think, or maybe KRC. I don't remember whether KRC had types. By the time they got to Miranda, they had types, and were beginning to do type inference, which makes certain kinds of pure functional restrictions more palatable. Because now you can, so for example, I would bring out the dreaded M word, the monad word. Without type classes and the ability to overload the bind operator, monads become incredibly oppressive way. They're algebraically clean.
Right.
You get the the guarantees of pure functionality, but you've got to haul around these extra arguments and just pull them out and stick them in and pull them out.
Right. Or deal with some restricted view of monads where a monad can be active at a time, but they don't really compose as well as.
Right. And then Haskell has some pitfalls in there. If you're putting two monads together, there are places where it doesn't know from the program text which one you're trying to party in.
Right.
I think it's the monomorphism restriction or something like that.
So Clojure is definitely coming from the Lisp tradition, walking towards more a functional style of programming. It's definitely not from the Haskell Miranda tradition.
Right. Now, would you say that it is it's easy to write a pure functional program if you want to? And is it easy to know when you are leaving the world of pure functions in Clojure?
Yes, it's easy to write a functional program or write portions of your program functionally.
Right.
And there's no help whatsoever in terms of knowing when you've done that correctly or not.
Right.
Right. So being dynamically typed, there's no types enforcing the lack of I/O or the presence of I/O or anything about that.
Right.
You can freely use Java mutable things and .NET mutable things, and if you do, they have the same issues they always did.
Okay.
And it's an important thing for people to be able to do that. So no, it does not try to track through a type system when things are purely functional, when they're not.
Right, and not even through a dynamic type system. There would be some ways that you might be able to track that dynamically, but
unfortunately, doing so would require sort of flagging most of the .NET and Java frameworks as dangerous by default, and reducing the utility. I mean, reaching those frameworks and leveraging those libraries is a big plus for Clojure.
It's a huge plus, and if you're in a pure functional world, you have to wrap them in monads or something like that.
Yes. Right. So in practice, what's happened, the thing that Clojure does is it gives you these really easy to use immutable data structures as the default thing. So unlike traditional Lisps, where really the only data structure you had in the syntax was a list. Most Lisps or schemes also had hash tables and things like that, but they didn't have recursive definitions like lists do. Right. A list, you add to the front and you can share the tail, if you're not mutating it. But hash tables, for instance, in Common Lisp are just like Java ones. You just bang on them and they change in place. So Clojure extends the homoiconicity of Lisp to the other data types. So there are literal representations for maps and sets and vectors.
Oh, very nice.
All of which are immutable and all of which are persistent. I mean, they do have recursive definitions.
Right.
They are based on tree structures and they support efficiently making new changed versions.
Right.
So you have syntax for all of that, which is nice. A lot more like Python or Ruby, where you have syntax for maps and well, they call them hashes.
When you say a map, do you mean a name-value pair?
I mean, like a
like
dictionary.
an association
Correct.
list.
Right. So there are literals for all those things. When you use them, you end up with something immutable.
Right.
So immediately, you're handed all these immutable things. Then you're handed this library that knows how to manipulate them, and so using them is idiomatic. So automatically, you start off and you're doing this, and for most of the calculation part of your program, you can happily stay there.
Right.
And then you have, okay, now I need to put something on the screen. I need to write something to the disk. I need to stick it in the database.
Right.
Those are all I/O things.
Right.
And if you look at the libraries of Java and .NET, a substantial portion of those libraries, the value in those libraries is I/O.
Yes.
It's getting stuff in and out of XML, getting stuff in and out of these data formats. Talking to a web server.
Right.
All I/O.
Plumbing.
So that's all great. Just use it.
What about numerics? Do you have any special numeric capabilities in Clojure?
It has the traditional Lisp things, which is the math is good.
Big num.
Big nums. Integer arithmetic doesn't wrap around.
Right.
The integers will just continue to grow. There's real rationals, so you can say 22/7, and that doesn't turn into point.
Okay, good. Exact rationals.
It stays right. It stays exact. So it's not the same kind of numeric tower as Scheme. Scheme had a much stronger sense of exact and inexact than Common Lisp. It's more in the Common Lisp tradition. But basically, by default, you won't lose any information by using
How about any
math.
symbolic capability, such as simplifying symbolic expressions?
That's not built in, but
Not built
like
in.
Lisp, you could,
not-
Maxima was written in Lisp.
Not so hard to add. Yeah,
Right.
That's
Right.
one of the
People
lovely
can do
things
that.
about Lisp. Is
Right.
it's part of what makes it suitable for writing compilers and program transformations.
Right.
Also makes it suitable for doing symbolic calculations in algebra and calculus.
Right.
So you're just doing symbolic calculations.
Right. So there's already a project called Incantor for Clojure, which is like an R-like statistics language.
Right.
And so writing those kinds of languages in a Lisp is really easy and a lot of fun. And because there's a transparent extensibility to the underlying language, there's no bridging necessary. You can intermix Incantor R-like statistics code and Clojure code.
Is it Cantor, C-A-N-T-O-R?
Incantor, I-N-C-A-N-T-E-R.
E-R, okay.
Yeah.
Right. It could be a pun on the mathematician Cantor.
No, I don't think it is, but...
Do you feel comfortable writing some stuff on the board? We've been talking abstract because you and I both have pictures in our minds of what this stuff might look like. But for those who don't know Lisp, let's write a few expressions.
Okay.
And,
Have we a pen?
We got some markers here.
All right.
With some luck. Here we go. Yes. And,
so Lisp is.
Let's see what some stuff looks like. First, a list and an ordinary calculation, and then I want to see what maps and sets and all these other groovy things look like.
Okay, so if we say +1, 2, we'll get 3.
Good.
There are no commas, there's no semicolons or anything like that. It's prefix notation.
Yes.
So the operator comes first, and then any arguments follow.
Great.
By default, the interpretation of things in parens is a list.
Yes.
So I've already talked a little bit about evaluation, but essentially, this is a list of 3 things.
Right.
This is a vector of 3 numbers.
Okay.
Okay. This is a map that's a curly. This is a map with 2 entries.
Good.
This is a keyword and a number, a keyword and a number.
Okay.
You could write maps from strings to vectors, or a vector to...
So they're arbitrarily nestable.
Arbitrarily nestable.
Very nice.
Like that.
Okay.
So list, vector, map. There's also sets, which precede the curly with the sharp. A, B, C.
Okay, and
So-
presume these are the usual set semantics where if you put duplicates in there, they get
get
washed
one
out,
only.
and there's no
Correct.
order.
There's no order.
Now,
That's
how does
right.
a list differ from a vector?
A list differs from a vector in the complexity characteristics of different operations.
Okay.
So a list is the very traditional Lisp list. It's a singly linked list where it's
Right.
efficient to add things to the front
Yes.
in an operation called cons, is construct.
Yes.
That's old school. So if we were to cons onto the beginning of a list, we would get a list with that new thing on the front.
Right.
But looking up the 14th thing in a list is a linear operation because you have
Right.
to walk the chain.
Right.
So the complexity characteristics of insertion at the front is big O1, looking up in the middle is big O(n). It's linear time. Adding at the end is linear time. It's terrible.
Yeah.
It's just not good for that.
Right.
It's good for adding at the front, and most everything else is linear.
But that also means it's good for recursive definitions, where you say do something to the first and then do something to the rest.
But all of these data structures are immutable and persistent. So vector has efficient adding to the end. In addition, it has efficient lookup by index.
What's the syntax for looking up in a vector, by the way?
It's well, vectors and maps are functions.
Yes.
Right?
Right. So you just call it on its index. Beautiful. Love it.
Or you could say get or nth, and there's a bunch of other things.
Sure, some little helpers.
There's a
but
bunch
that's the primary idea there. It's just another. It's just a function
Correct.
from its index
so
space
I could
to
also
its,
do this and get one.
This colon operation is a little interesting. What
Okay,
is that?
so there's a couple of other primitives that we're not talking about here. This is a literal for a number.
Yes.
This is a literal for a keyword,
Okay.
which is essentially like a symbol. Actually, I should do these first. That's a literal for a symbol,
All right.
which is like a string, except you don't have to put it in double quotes, and it's distinct from strings.
Okay.
So the symbol A is different from the string A, is different from the keyword A.
And you don't have to put tick marks the way you used to have to do in old Lisp, right?
Well, you would if you asked to evaluate A.
Okay.
Right? Now all of a sudden you're asking for the interpretation of A in a
Okay,
context.
I see.
And in which case, if you just wanted the symbol, you could quote it.
All right. Good.
Essentially, the difference, a symbol might stand for something else in use in a program.
Mm-hmm.
A keyword only ever designates itself.
Good. Okay.
That's the distinction between
Right.
keywords and symbols. And strings are strings. In fact, this string is a Java string on Java. It's a CLR string on the CLR.
Nice.
There's no wrappers. There's none of that
It doesn't
stuff.
turn into a list of characters.
No, it does
Yeah,
not.
right.
But you could treat it as one. For instance, you could map a function across a string.
Okay, good.
But we're skipping way ahead.
Yeah, it's all right. We'll jump around here.
So there are literals for all the data structures, right?
Right.
And then there's and what happens is you write a program by writing data structures, right?
Well, this is very. I just want to before we go there, I want to point out. This is very. I want to point out two things I noticed. One is this is very nice. This is really. It's not just name value pairs. It's an arbitrary discrete map, where the domain on the left, the domain is any of the values that you're
Correct.
allowed to have, and the domain on the right is any of the values you're allowed to have.
Correct.
So that's lovely.
That's right.
And the
Everything
second thing
is.
about the prefix notation, that really is a direct representation of abstract syntax trees. When you start nesting those things,
Right.
that turns into ASTs.
That's right.
And this is why people, when XML came out, the old timers said this is
What's the
nothing
big
but
deal?
Lisp with
Right. With
noisy
more-
Lisp.
Right.
And the XMLer says, what's this Lisp thing? That's
Right.
hiding the structure, but it's just trees.
Right. So you write a program mostly by writing literal representations of lists in your program.
Right.
And some vectors as well are used in the syntax. In addition, if you want to create a map or a set, you might use a literal version of those. But the important thing about Lisps is that the language is not defined in terms of syntax, defined in terms of characters. It's a two-phase syntax. There is your source code, right?
Right.
Then there's something called a reader. And the source code is text. What the reader outputs is data.
Right.
So the reader will read this and will read the symbol plus a list of
Yeah.
the symbol plus the number 1 and the number 2.
Right.
And that's what the reader will produce, is actually an in-memory data structure of that list.
Right.
And that data structure is then passed to the evaluator or the compiler, which will maybe do something about it.
Mm-hmm.
The critical thing is, so you can put your code in a file and take the text and put it into the reader, get the data out, and that's what happens automatically. If you say load file, all this stuff
Right,
happens, and
right.
this gets handed to the compiler. But you could also have some program that you wrote, right, produce data directly
Yep.
and hand that.
And from that point on, you can't tell the difference.
It cannot tell the difference. It never needed to be in a file. In addition, the evaluator can go and say, hey, I've gotten this data. What do you think about it?
Mm-hmm.
And get new data back. And that's
Right.
how macros work.
Right. Right. Beautiful.
So it's a really beautiful thing. So we write our code in terms of data structure literals. We don't need JSON or XML because we can send all these things. They all print and they all read correctly.
Yes. Right.
So the syntax for the literals is the syntax for the language. It happens to be that when the evaluator sees a list, it tries to interpret the first thing in the list as a function of some sort,
Right.
and the rest of it as a call to that function.
Right.
It interprets a literal vector as a literal vector and maps as maps. It
Right.
treats most of the rest of them as data,
Right.
but treats the lists as calls.
Right. And that's why you need tick mark for something like this.
If you wanted to treat this as data, you would do this.
Yeah.
But it's idiomatic Clojure to use a vector instead.
Okay, very nice.
So vectors have fast lookup by index.
Yeah.
They have fast insertion at the end.
Right.
But because they are persistent data structures, you can write a recursive algorithm or say an exploratory algorithm that conditionally builds vectors and maybe you throw them away. Right? But
Backtracks over them, yeah,
backtracking
right,
is
yeah,
easy
right.
because you're not actually destroying it. So there used to be an operation called cons that added to the beginning of a list.
Right.
That's been abstracted into something called conj in Clojure,
Nice.
which will add to anything
Yes.
in the way that's appropriate to that thing.
Yes.
So you can conj onto this, it will add it at the front. If you conj onto that, it will add it at the end. If you conj onto this, it'll add the key value pair, and
Yeah.
you can conj onto the set. So you can write generic algorithms, like given any kind of data structure, any one of these data structures, you can say into that data structure, some collection, map a function across some other collection.
Right.
This works for every single one of these. Into is defined in terms of conj. It's reduce with conj. So you can build collections generically, and reduce is done recursively, right? And map
Very nice.
works on any collection. So all the collections can be treated as if they were lists. They aren't structurally,
Right.
but they support a sequence interface.
Yes.
So that gets to the next part of Clojure is that there are interfaces for all these things. And they're
Okay.
normal Java or .NET interfaces.
Right.
So all of these are lifted to an abstraction represented by an interface. So there's an interface for associativity, which applies actually to both of these things, right? Because it's
It's just a special
associative
map,
lookup.
yeah, right.
There's an interface for whether or not things are countable in constant time. There's an interface for sequentiality, which is possessed by this but not that.
Right.
And so there's a big hierarchy of abstractions that are underneath this, which means it supports multiple implementations. I provide sorted, a red-black tree behind this and a
Yeah.
special hash array mapped try version of this, but you can write your own.
Right.
And the same code will work
Right.
for you.
All you have to do is implement that interface, and
Correct.
Then into
Then
map,
this
and all
works.
these dudes will work.
Correct.
Does that also mean that it's easy for JVM and CLR programs to invoke the evaluator?
Yeah, sure.
Okay, so you've
So-
got complete bidirectional,
Yes. Yes.
what we used to call foreign function interface, but it's
Yeah,
not so foreign.
It's very
here.
not foreign. So we could look at that if you wanted to say, two upper on a string. I'm running out of space here. Actually.
Oh yeah, let me
Erase
give you
a little bit.
give you the eraser.
Which side? This side?
We're violating immutability here.
There we go. Is it two upper?
Yeah, let's pretend it
Uppercase?
is. Yeah.
Somebody remind me of the syntax. So there's some special syntax for host interop.
Right.
So we can call a method on an object using dot, which is actually connected to that symbol.
Right.
We can call, some static thing like that.
Mm-hmm.
You can call new by saying new, my class, or just my class again to get back to sort of treating it like a function.
Right.
So that's interop,
Yep.
and it's very transparent.
Now, it also brings us into the realm of mutable versus immutable. Your basic data structures are immutable, meaning
Immutable.
that functions that perform transformations on them don't destroy the data.
Correct.
But these guys are, of course, perforce mutable, and
Yes.
very observably so.
Depends on which they are, but like
Well,
string
yes,
isn't.
right, but in general they're mutable.
Potentially, right.
And you have to, the style of programming is completely different. why don't we get into that? Because one of the things where I'd like to end up is I'd like to understand the Clojure concept of identities.
Okay.
And how we navigate the waters of the mutable world, which has one sort of feel, style, intuition
Right.
that's appropriate for it, and the immutable world, which is less familiar to the average programmer, but has its own sort of conceptual clarity that is very attractive to some people. And Clojure's doing both. And how do we navigate between those waters, and where does this identity concept, which I don't understand. I want to understand the identity concept first of all, and then I want to understand how it fits into these mixed waters that I also understand. It's sort of like the Blue Nile flowing into the White Nile here. Yeah.
Well, the first thing I would want to explain is what I'm talking about when I say persistent data structure. Good. Because I think it's one thing to tell somebody something is immutable and they can't change it, in which case they say, that doesn't seem very useful to me.
Of course.
And to give them a recipe for working with immutable things that's both efficient and convenient.
Right.
And so what a persistent data structure is not merely immutable. A persistent data structure has another special characteristic. So we're not talking about persistence meaning you can put it on the disk in a database. Right. We're talking about persistence in this case, which means essentially if you take some immutable thing and you produce a new version of it, several things will be true. The old version will remain accessible. You can produce the new version in compliance with whatever the complexity guarantees are for that data structure. Right. So if I say you can put something at the end of a vector in constant time, then doing that, even though it's producing a new vector, must happen in constant time. Right. Which implies something immediately. Yeah. It can't be copying the entire vector. Right. Because if it were to be doing that, it wouldn't be meeting its complexity guarantees. It would be linear then. Right. So
that
making
implies there's sharing going on underneath.
Right. So there's a bunch of implications from this, but the guarantees are that the old version will remain accessible, that the new version can be produced while meeting the complexity guarantees, and that both the old and new versions, after making a new version, will also meet the complexity guarantees. Because there are some people who have attempted in the past to sort of cheat, to make versions where the latest version is as fast as you expect, but older versions kind of decay. You know, so there's no cheating going on in Clojure data structures. They're really persistent, so they meet the complexity guarantees, even old versions. So how could you possibly do this? Right? How could you make a vector where you could add something to the end in constant time? And the way you do it is that it obviously can't be a big array.
No.
Right. It has to be a tree.
Yes.
So the real secret is all of these data structures, except for the list, which can meet its guarantees by just being a singly linked list, are trees. And part of the work of designing Clojure, for me, was to make versions of hash maps. So what you get by doing this is a hash map. Right. It's not a red-black tree. Okay. I have red-black trees, so if you want a sorted version, you have that. Right. But this is a hash map, and this obviously has constant time or near constant time expectations. Right. So making them fast was a critical objective of Clojure. So the trees that underlie them are extremely shallow. They have very high branching factors. Right. So what it means is to produce a new vector that's represented as a tree means that vectors are segmented, right? At the leaves of these trees are arrays. Okay, good. Okay. So now you can imagine. It looks a
little bit like a trie then.
It is a trie.
Oh, okay, very good.
You know, some people pronounce it tree.
I don't know how to. Yeah,
so right. Yeah, right. These
TRIE.
Hash array mapped tries, and the reference is Bagwell. So Bagwell, did these. Bagwell did hash tables this way, non-persistently, non-immutably. Right. And so what I did was make immutable versions that were fast enough. And then the vectors are not really hash array maps, but they end up being in leaves of a tree. Right. Where you can access them by using their index to find the right path. Right. The branching factor is 32, so they're extremely shallow. Yep. But what does it mean to add to the end of this? It means you're going to take the last array, right? Mm-hmm. You're going to copy it, right? And since it's got a bounded size of 32. That's constant time.
Yep.
Right? And then you're going to copy the path to the root.
Okay.
So you're going to end up with a new root, right, and a new path down the right side.
Yes.
The thing has been added to this.
Yes.
But the rest of this will all share, right?
Nice.
This tree, this new tree, will share everything else.
Right.
So if this thing has 1 million items in it, you're going to change 3 nodes on the right side to add
Right.
something to the
Right.
end.
Right.
And that makes that efficient.
Very near constant time.
Right. Right, so that makes that efficient, and so that's called structural sharing. So persistent data structures have structural sharing, which means that you can make a new version and it's inexpensive to do so.
Right.
And that's how you program. Instead of saying, change this thing in place, you say, call this transformation function, which makes a new thing, and give me that.
Yep.
And of course, that changes your life, because
Right.
then you can share these things in ways you could never share objects.
Right.
Because an object, you don't know, is this going to be okay? Can I remember this? Do I need to clone it?
Yeah.
You know,
don't know
if there's
what
concurrency involved, it's a catastrophe.
All bets are off. Right.
Right. So that's not true. You can always use one of these because they are immutable with no synchronization whatsoever.
Well, let me stress this a little bit. When you say the old version is accessible, what that means practically is that if some variable is bound to
Correct.
that old version, and you reference that variable, you will
You're
still
still
get
good.
the old things. That means you can
You'll still
trust
get it, right.
the computations that you've already done.
Right.
It means the compiler can make deductions based on those, on simple textual
Right.
analysis of the program, and say this part over here is safe, that part over here is safe, and I can allocate one thread to one and another thread to the other, and they'll never collide.
With more help, it probably could. I mean, theoretically,
In
a
theoretically,
system,
yeah.
right, in a
Right.
system that conveyed the fact that this was immutable and I'm handing it to you that way,
Right,
you can continue that process.
Right.
In practice, Clojure does not do that.
Right.
It just gives you these data structures and the confidence in you can call this function, it won't change what you've got in hand. You
Right.
can freely alias things
Right.
because they can't change.
Right.
You can build recursive undo. What could be easier now?
Yeah.
What's undo? It's just keep track of the old roots of this tree.
Right. And all the
You
old
know,
backtracking algorithms. from
Everything
games
works
and whatnot.
beautifully,
Yeah,
right? So a lot of the old Lisp algorithms, which really could only work on lists,
Yeah.
now could work on sets.
Yeah.
You could do a search with sets, past sets,
Yeah,
build
so
them
the
up.
old iSetL language it seems as completely incorporated in
Right,
here.
that kind of thing you can do here, yes.
Yeah, beautiful. All right, now let's get into the, if it's the right thing to do, if it's the right time to get into that, let's get into these identities. What are
Okay.
these critters?
Okay, so Clojure is not object-oriented.
Right.
And it's not Clojure is sort of a response to the challenges I faced trying to build these big,
Right.
multi-threaded systems using object orientation. I mean, eventually my programs became really functional, even C# programs, just
Yeah.
as a self-defense mechanism.
Right, right.
But of course, it's very much not idiomatic to do that.
Right.
And so in my thinking recently, I've tried to tease out a couple of things that underlie object orientation that I think aren't working quite correctly. And one is that object orientation conflates identity and value.
Okay.
Right? They're bound together. If you have some object, you have something you'd like to reference over time, but its value also could change over time. There's no distinction between, Fred, the thing I want to remember, and the value of Fred at any particular instance of time. There's no distinguishing those because the object reference is essentially an alias for a block of memory somewhere.
Right, and when you look at it, when you reference it, you don't have any idea.
You have no idea what you're going to get.
And that's the difficult, the challenge of concurrent programming is timing the access to things.
That's one way to think about it.
Right.
So I have a picture in my presentation where there's a bunch of references to some object. We'll call him Fred. And they call him Fred. They like that.
Yeah.
And the problem is that there's no changing Fred without potentially undermining anyone observing it.
Right.
They not only have the identity, right, which is an important thing. And identity is an important thing, Brian.
Sure.
Right. Well, you're not the same from moment to moment.
No.
Yet
But my public key might be the same.
something about you is
right.
the same because we can continue to refer to you that way.
Right.
So that's what identity is about. It's
Right.
not necessarily your name. You could change your name, but we could all remember, well, he used to be called Brian, now he's calling himself Fred.
Yeah.
So it's not actually the name. It's the label we give to the continuous set of states you're going to take on.
Right. It's
Okay.
actually a label for a timeline, in a way.
Exactly.
Yes.
It is a label for a timeline. So, so this is broken. Okay, it's broken in a big way because it conflates identity with state. This is a label associated with this block of memory
With a state
forever and ever.
instead of a label associated with a timeline.
Right. So how can we fix this? What we can do is we can say, we're never going to let these things change. These are values. Right? This is a pile of memory. It has really no logical support.
Right.
It's not really a value. It's not really a time series of values. It's just cubbyholes somewhere.
Right.
And it's very hard to think about it.
Very.
So it's very easy to think about a value. All these things, they can't change.
Right.
So we can imagine some version of Fred at some point in time that's this value,
Snapshot.
FV1.
Yeah. And it could be a big complicated thing like this.
Absolutely.
But its behavior over time is essentially
It has
simple.
it has no behavior over time.
Right. So it
doesn't
couldn't be any
behave.
simpler, right?
It's a value. And instead what Clojure does is going to say, you can put your identity concept over here.
Okay.
You can label this box
Yeah.
Fred. And so Clojure has a set of reference types,
Okay.
which are distinct from these value types.
Right.
And all they are boxes,
Okay.
right? And the boxes always refer to values.
Okay.
Okay. So what is this box? This box is a time management unit.
Okay. Good.
Okay. And so it ends up you can have a variety of different semantics for managing time, for managing the succession of values that you're going to call Fred.
Okay.
So let's say we want to change Fred's something. There's a date of birth here, and there's some value. We want to change it.
Change it,
We
all
had it
right.
wrong.
Yeah.
So we need to change it. So what we're going to do is we're going to call some function on this value
Yeah.
to produce another value,
Yep.
okay, which will be the Fred's value too.
Yep.
And because we're going to use these persistent data structures and the functions on them, producing this new value won't change that one.
Right.
So we can be doing this at any time, and anybody who is looking at this is completely unaffected by that.
Right.
So we fix the date of birth here, and now it's better.
Yep.
Right. At some point, we want to say, all right, this should be the value that people use when they refer to Fred.
Right.
With the new thing. So what happens is we have a way to atomically say, this is now what Fred is.
Okay.
Which means if you were thinking about this, what happened to you?
Well, if I have a variable bound to it, that's still okay.
No,
But
absolutely
if I'm referring to it through Fred,
But you're not.
I'm- yeah,
If you're in the middle of some computation using this value,
everything's fine.
you're completely unaffected by this.
Right.
You cannot be affected by this.
Right.
In fact, you can remember this forever.
Yeah.
I loved it when Fred was born on this date.
Yeah,
I
I
hated when he
just-
changed
yeah,
his
yeah.
date of birth.
He's
And then-
lying anyway.
He was lying, right?
Yeah.
That wasn't a good feature to change. Maybe his occupation changed
Yeah,
or
but
something
we
like
get
that.
it, yeah.
So these are two independent things, right? So you do your calculations on values.
Yes.
And producing this version, maybe this is an elaborate thing. Maybe it's not
Right.
just set date of birth equals something
Right.
new, but some elaborate transformation. It doesn't matter. It's going to take one value and return another.
Right.
The readers can never be impacted. In addition, they don't hold up this operation either. The fact that someone's reading this value doesn't impede somebody making the next value of Fred. And so all you care about is that this reference manages time well.
Now, is it fair to say that the reference is just a special kind of variable?
It is a special kind of variable because because variable is another one of these empty concepts,
Yeah.
right, with no semantics.
Right.
So what does it mean to be a time construct,
Right.
right? It means you have to ensure a succession of values. Right? So the first key is there's only going to ever have in it a reference to a value.
Right.
Right? That succession has to be atomic. Right? The value inside has to be visible. Okay, in other words, I can ask for what's in Fred. So there's you can say at Fred in Clojure.
Right. Okay.
So they're a lot like ML references. ML had one mutable thing, other than arrays,
Yeah.
which was a ref type. And that's what inspired this. The problem is
Okay.
even ML's ref type does not have semantics for time.
Right.
So the semantics for time say, how are you going to make sure this is the case? Right? If two people go in and try to muck with this, how are we going to make sure
That they
you know,
know,
that's
yeah.
going to work?
Yeah.
And it ends up that there are multiple semantics for managing time.
Okay.
One of the simplest ones is CAS, just compare and swap. Compare and swap is a single timeline, uncoordinatable time management system.
Right.
It basically says there's going to be a succession of states here. I'm going to make sure that whoever's creating the next state is doing so as a function of the
Yeah.
immediately previous state. So
Right.
I can manage the succession.
Right. In the old
This-
Windows
this
lingo,
does-
that's interlock compare exchange.
I should say, all right, compare exchange.
Just for those who are Windows
Good,
literates.
right. I don't think that's what any CPU calls it, but.
Yeah, no.
Okay,
Test and
and
set,
then,
usually,
right,
yeah.
test and set, or, you know, yeah.
Okay.
So it can make sure that's atomic, and of course you can just read out of it, which means you're only going to see the value at a particular point in time. You
Right.
don't know immediately after that it could change.
Right.
And we should become happy with this, because in the concurrent world, there's a lot more is going to work this way.
Yeah.
So it ends up, you can do a lot with CAS-like semantics
Very traditional.
for time.
Right.
Right. That's way better than a variable already, because
Yes.
a variable, you never know that things are going to be atomic. You don't know that one value
It's
is
intolerable,
the
yeah.
successor of another.
It can
So-
be partly changed, and
Right.
you know, it can be.
So Clojure has
impossible.
a construct that wraps this whole thing. It's called an atom. It's
Okay.
the simplest time management construct. It uses CAS internally.
Right.
It does the spin swap automatically, so that every value is a guaranteed function of the immediate preceding value.
Okay.
If it's not, your CAS is going to fail, and you're going to have to do over.
Right.
But you can't do things like transfer information between bank accounts like this.
It's non-transactional. Yep.
Right. Well, it only deals with a single thing, so it's
Right.
isolated.
Right.
Right. So a lot of times you need to make changes to the world that are coordinated. So there's also a coordinated reference type in Clojure, which is called a ref,
Okay.
and that is transactional. Those references can only be altered inside a transaction.
Okay.
So if I go and I have an atom, I can say swap and pass it a function. So it's a beautiful thing, the way these things look. Oops, I'm falling apart here. The way these things look is if I have an atom, I can say swap my atom, some function, maybe some args,
Okay.
right? The function will be applied to the, function will be applied to the current value
Right.
with the args, and that will become
The new value.
the value, the next
yeah,
value.
Yeah. Yeah.
Okay, so there are also references which are transactional. They look very similar. You say alter some ref, which is now one of these transactional things. Again, you pass it a function and some args, right? And maybe you want to do this to, two guys. Alter ref 1 this way, alter ref 2 some other way, right?
Right.
Okay, so you do this. That fails. Why? You didn't start a transaction.
Ah, okay. The coordination. Yes.
Right. So we say do sync around this.
That's nice.
And now that succeeds. Either all succeeds together or not
the
at all.
usual transaction.
Acid kind of things, except it's
Now,
not
how
durable.
do you find out whether it succeeded or not? Or is it just when do sync returns, it's guaranteed succeeded, or it can't be? You got to have the.
The do sync, the transactions will retry automatically.
They'll retry automatically.
Correct.
Okay. So when do
Right.
sync is finished.
Without exceptions, it's done what you want.
Okay. Exceptions is the way to find out.
Exceptions
that it
can flow out. I mean, if you actually had
Yeah.
an exceptional problem. If your problem was only that you couldn't get a synchronized view of these two things,
Right.
that will automatically be retried.
Okay,
so
good.
retries for synchronization happen automatically.
But if you get an exception out of here, there's a rollback.
You had
underneath
something
it,
right.
so yeah,
None,
okay.
It didn't happen.
Good.
Nothing
Beautiful.
happened.
Yes.
So you have those semantics, which looks very similar. So it's a model based around references or time coordinators that ensure a succession of values, that each value is a function of the last.
Right.
There are different semantics for it, coordinated or uncoordinated. There's also an asynchronous version, which is a lot like the atom, except when you ask for the change to be made, that returns immediately, and the change happens sometime later on a thread pool.
Okay. And how do you pick up notification of the change? A
You don't.
callback, or you don't?
You don't. I
It's
mean, you can,
blind.
you can, but by default you wouldn't. It's a style of programming like Erlang's, right, where
Right.
you want to stop caring about that. Again, your emphasis should be away from the transactional. The transactional sort of old school. Stop the world. I want to own the computer.
Right.
Right. It doesn't actually stop the world. It supports multiple simultaneous transactions. If they don't conflict, they can both succeed in parallel.
Right.
But you want to move, as things get more and more concurrent, to a world in which you want to care a lot less, right?
More fire and forget.
More, sort of fire and forget, or yes, or you build communication infrastructures. But the beautiful thing about these time units is that they support like a uniform way to be notified when something changes. That does exist, and you can get it for any of them.
Right.
You can also, in a uniform way, supply validators that say, these are the set of values I would accept here,
Right.
and provide an arbitrary thunk of code that will ensure that things that get put there are okay by you.
Now, we went over how these things are used with the immutable or persistent
Yes.
data structures in Clojure. What if you're trying to use these with things that you
don't use
you
these
don't
with
use
those.
them? Okay, very good, very good,
Don't
very
use
nice.
this. Because it's sort of essential. Now, the reason why I wanted to talk about the persistent data structures is it's quite essential that this be inexpensive and not disturb that.
Yeah.
Because now we just saw, well, it might get retried.
Oops.
It might be done speculatively, right?
Right, right.
And also it needs to be the case that readers don't get impacted by these things. So
Right.
they go together.
Right.
There's no taking this cool reference
Yes.
identity thing
Yes.
and making it work with something mutable.
Well, I could actually imagine a variant of Clojure, call it Clojure minus minus, that is purely functional, has only these persistent structures, but also has this reference idea and
Right.
doesn't have the mutable data structures that are.
You definitely could do that.
So it would be a restricted thing that doesn't
Right.
have the beautiful foreign function interface,
Right.
but it would all be clean and.
Yes.
Yeah. Okay. Good.
Yes.
Well, there are a couple of areas that if we had a couple more hours, I would love to explore, and those would be. We recently have the new reactive framework in .NET, which is iObserver and iObservable, and I see some similarities between the succession of values over
Yes.
time and the iObserver, how an iObserver
Yes.
gets notified. And I tend to think of those as elaborate callbacks, but they're really a variation of the continuation monad or a variation of the old continuation passing style, which took off like a lead balloon in the Lisp world. But still, there are some very pretty ideas, and I think iObserver and iObservable have done a beautiful job of fixing that in .NET. I'd love to be able to explore that at length. And the other is Time Warp, which is one of my old hobby horses, which was a whole operating system built on speculative execution.
Okay.
Sequences of operations specified with respect to virtual time, with a mapping to real time that affected rollback and commitment, with a deep analogy to virtual memory. So your entire program was really just a space-time coordinate system
Yes.
in which events took place events were specified in virtual address space and virtual time space, but were realized in real time and in real address space by page fault or time fault.
Okay.
A time fault being a rollback. And it seems like there are some great touch points that we could
Definitely,
go
it's
into,
all
go into
connected.
there. I'm not sure whether it would be a cool idea to try to write Time Warp in Clojure or to try to write Clojure on top of Time Warp or vice versa. So that's why I think we would need a couple of more hours to play around with it. But I'm really happy. I get it. I love it. I think this is another great piece of work in the, of course, being a partisan in the .NET arsenal, but it's also in the Java VM arsenal, and I love it. It's the kind of thing that I would definitely use this afternoon.
All right. Great.
Thank you very much.
Sure. Thanks.